All right, so here we are in chapter 1, which is matter and measurement. So section 1.1 is the study of chemistry. 1.2 is classifications of matter. So what we'll be learning in just this section, we'll go through learning target 1.1. I can classify matter and its changes based on its properties. 2 of the subtargets we'll cover. A, I can define states of matter and distinguish their properties, as well as B, I can classify materials as elements, compounds, or mixtures, stating evidence for that classification. That's what we're going to do in this section of the podcast. So one of the big questions is, why are we here in this chemistry class? Chemistry is the study of matter, its properties, and interactions, which is important, with other matter and energy. So when we talk about composition, that's what it's made of. Structure is how it's put together. And changes is what it does. If you look at our picture here, chemistry is really in the middle of all of it. So in all these other disciplines that we have here, chemistry really is kind of a central discipline that allows you to branch out into things like biology, biochemistry, medicine, if you're interested in that. If you want to go more of an earth science, you could do geology, environmental, plant science. But you really do need to have a pretty strong background in chemistry in order to do any of those things. So what is matter? Matter is anything that has mass and takes up space. So mass is the amount of matter in an object. Space is the volume that's occupied by that object. So then what isn't matter? If matter is anything that has any mass and takes up any amount of space, what's left over that doesn't fall into that category? So how do we see chemistry? We see it on the macroscopic scale, which is ordinary sized objects, the things that you can see with your eyes around you every day. So for example, we'll do an experiment in lab and we get to see the result of the reaction. So we make our observations on the macroscopic scale. The microscopic scale is the realm of atoms and molecules. So a lot of times you'll hear me say, put on your atom goggles. You have to start thinking about what are the atoms and the molecules doing, not just what are you seeing on the macroscopic scale. So using your observations from the macroscopic, you can draw conclusions about the microscopic. So the macroscopic allows you to draw conclusions on the microscopic. So what are the states of matter that you'll be responsible for? We have the gas state of matter. Fills the maximum volume that you allow it. We call that indefinite volume. It diffuses or spreads out to take the shape of the container, so it also has indefinite shape. It is fluid and compressible. So fluid meaning that it moves rather easily, and compressible means you can smush all the molecules even closer together. Vapor is typically used interchangeably with gas, though it does have a slightly different meaning. A vapor is a gas that is usually a liquid or a solid at room temperature. That's why we call it water vapor and not water gas, because water happens to be a liquid at room temperature. There's low attraction between the particles, which means they're separated by great distances. Then we have liquids. They have a definite volume, so they have a volume that can be measured. They take the shape of whatever portion of the container they happen to be in, so that's an indefinite shape, which is something that it has in common with gases. There's medium attraction between particles, which means they're close together, but they can slide past one another. Lastly, we've got solid. They have definite volume and shape, so they hold their own volume, can be measured, and they hold their own shape. There's high attraction between particles, which means they're packed very tightly together. So you can see we have over here, this would be the gas state. So we can see, for example, the molecules are spread pretty far apart from one another. There's lots of empty space here. They're moving very fast. They have very low attraction for one another. That would be like up here in the clouds. This is a bunch of water vapor all together. Then we have the liquid. Notice that they're much more tightly packed together, but they don't have any structure. You can't see any pattern. It looks kind of chaotic. That would be like down here in the liquid water. Notice they're tightly packed together, so that means they have high attraction or medium attraction. Then we have over here the solid. Notice that now we're starting to take on a very defined structure. That would be like our iceberg up here. The solids do have a very definite shape and volume. You can see that up in the iceberg, it's holding its own shape. You can also measure its volume. They're packed very tightly together. They have very high attraction, so much so that they've actually organized themselves into this nice kind of repeating pattern. So let's talk about classifying matter. Matter can be classified as either a substance or a mixture. So we'll start kind of on the more basic side, which would be a substance, and then we'll move over to more complicated, which would be the mixture. So substances can also be broken down into two categories, the first of which is called an element. That would be the simplest form of matter. Contains only one type of atom. That means you can't break it down any further and still be the same element. So for example, anything in our periodic table of the elements, gold, which has the symbol Au, iron, Fe, hydrogen, which is H, or mercury, which is Hg. You can actually see over here in our picture, there is only one type of atom that is present. Over here, it's still one type of atom, though there might be two of them joined together. We call that diatomic, or two atoms that like to hang out together. Hydrogen is one really good example of an element that behaves diatomically. Next, you would have the compound. A little bit more complicated, and that's because it's more than one type of atom or element. And they're joined together chemically, which means that if you want to decompose or break them down, you have to either use a chemical reaction to break it apart, or electricity or energy in order to break it down into its elements. It also has what's called a fixed composition, so it has a very distinct amount of each of the elements present. For example, water, we're very familiar with, is H2O. It's always two hydrogens combined with one oxygen. Something like table salt, NaCl. It has one Na and one Cl. Table sugar, C6H12O6. You can see that it has a very fixed composition. In order to be called table sugar, it has to have this formula. Now we can see that the atoms are joined together. We've got this purple in the middle. We've got some green on the outside. That's telling us that it is multiple types of atoms, but chemically bonded together. So chemically together, chemically apart. On the other side, we've got mixture, which is a physical blend of two or more substances. And if you physically put it together, you can separate it physically. These can then vary in composition. So for example, salt water is a type of mixture. It's not the same everywhere that you find salt water. Different oceans have different content of salt per water. If you make your own salt water, maybe you have a saltwater aquarium, they all have a different composition. So you can see over here in our picture that we have a compound. We also have an element. Here's another type of element. But then they're all physically put together. They're not bonded together. You can see these two are not touching, but they are physically mixed together. So two types of mixtures that we have. The first is called homogeneous, homo meaning the same. So there's uniform distribution of the particles throughout. They're spread nice and evenly, no matter where you take the sample from, the top versus the bottom, the left versus the right. You're going to get a uniform distribution of those particles. We also call homogeneous mixtures solutions. However, most people think that these homogeneous mixtures have to be in like what we would consider more of a liquid type state. That's not actually true. They can be solids, liquids, or gases. So for example, salt water, which we've already talked about, is a mixture of a solid in a liquid. We also have toothpaste that you brush your teeth with, hopefully, every morning. And that's got some solid particles that are suspended, and it also has some liquid. And then if you looked at an example of a gas, that would be like the air that you're breathing right now. It's a mixture of things like nitrogen and oxygen, carbon dioxide, water vapor. The other type of mixture is called heterogeneous, hetero meaning different, so it has non-uniform distribution of particles. It does have distinct phases, which means you can typically see them. That would be something like you can see particles floating around. You can see bubbles of gas, for example, that carbonated soda that you drink. You've got a liquid, but then you've got all those bubbles that are mixed in there. That actually means it's a heterogeneous solution because you can see those distinct phases. More examples, vegetable soup. Here we have a specific type of rock, and you can see that it has these veins of darker green, then it's got this lighter green, but it's not uniform throughout. Your Italian salad dressing, you know that you have to shake it before you can use it, and that's because all those solid particles like to settle out to the bottom. What you want to do is you want to make sure they're all nice and mixed up before you use it. Ores then are examples of metals in solids, and that would be, for example, when they mine for things like copper, you'll often see the rocks with kind of veins or pieces of copper running through them. All right, so here's your first practice problem. You're going to try and classify each of the following things as elements, compounds, homogeneous mixtures, or heterogeneous mixtures. So I do want you to write these down in your notes, and I'd like you to press pause, and I'd like you to look and see what each of these, try and guess what each of these is. So go ahead and pause here. All right, so hopefully you got a chance to answer some of those. Let's look at white gold. Is a homogeneous mixture. It's spread evenly throughout. You don't see any individual pieces. Aspirin is actually a compound. It has the formula C9H8O4. The actual tablets themselves, however, are homogeneous mixtures. So I could go either way on that. And that's because it's not just made up of aspirin, but it's made up of fillers and preservatives so that your aspirin doesn't go bad quickly. It's also made up of colors. So, you know, maybe to make it look more appealing or to print the name of whatever brand of aspirin that you use. So I could also go with homogeneous mixture on that. Iron is an element because it has a symbol off of our periodic table. A caramel macchiato from Starbucks, one of my weaknesses. You can see each of the individual pieces. So it is a heterogeneous mixture. Tap water is homogeneous. It's not just water. You've got anything that might have been in the pipes that was carrying it to your house. There's small amounts of metals, bacteria, all kinds of things that make their way into your tap water. And then the last one is brass. This is a hard one. You can't find it on the periodic table. And it doesn't have a distinct or uniform composition. That means that it's a homogeneous mixture. So it's actually made up of two elements, mixed together physically, which means you could physically take them apart. So it is not considered a compound, it's actually considered a mixture.